multi-threaded to take advantage of these new chips is likely to be the single greatest constraint on computer performance in the future. If developers are unable to design software to fully exploit the resources provided by multiple cores, then they will ultimately reach an insurmountable performance ceiling. The telecommunications market had been one of the first that needed a new design of parallel data path packet processing because there was a very quick adoption of these multiple core processors for the data path and the control plane. These MPUs are going to replace 19. The traditional network processors that were based on proprietary microcode or Pica code. Parallel programming techniques can benefit from multiple cores directly. Some existing parallel programming models such as SILC+, OpenMP, OpenHMPP, FastFlow, Scandium, MPI, and Elane can be used on multi-core platforms. Intel introduced a new abstraction for C++ parallelism called TBB. Other research efforts include the Codeplasive system, Cray's Chapel, Sun's Fortress, and IBM's X10. Multicore processing has also affected the ability of modern computational software development. Developers programming in newer languages might find that their modern languages do not support multicore functionality. This then requires the use of numerical libraries to access code written in languages like C and Fortran, which perform math computations faster than newer languages like C#. Intel's MKL and ACML are written in these native languages and take advantage of multi-core processing. Balancing the application workload across processors can be problematic, especially if they have different performance characteristics. There are different conceptual models to deal with the problem, for example using a coordination language and program building blocks, programming libraries or higher-order functions. Each block can have a different native implementation for each processor type. Users simply program using these abstractions and an intelligent compiler chooses the best implementation based on the context. 20. Managing concurrency acquires a central role in developing parallel applications. The basic steps in designing parallel applications are partitioning. The partitioning stage of a design is intended to expose opportunities for parallel execution. Hence, the focus is on defining a large number of small tasks in order to yield what is termed a fine-grained decomposition of a problem. Communication. The tasks generated by a partition are intended to execute concurrently but cannot, in general, execute independently. The computation to be performed in one task will typically acquire data associated with another task. Data must then be transferred between tasks so as to allow computation to proceed. This information flow is specified in the communication phase of a design. Agglomeration. In the third stage, development moves from the abstract toward the concrete. Developers revisit decisions made in the partitioning and communication phases with a view to tuning an algorithm that will execute efficiently on some class of parallel computer. In particular, developers consider whether it is useful to combine, or agglomerate, tasks identified by the partitioning phase, so as to provide a smaller number of tasks, each of greater size. They also determine whether it is worthwhile to replicate data and computation. Mapping. In the fourth and final stage of the design of parallel algorithms, the developers specify where each task is to execute. This mapping problem does not arise on uniprocessors or on shared memory computers that provide automatic task scheduling. On the other hand, on the server side, multi-core processors are ideal because they allow many users to connect to a site simultaneously and have independent threads of execution. This allows for web servers and application servers that have much better throughput. Licensing. Vendors may license some software per processor. This can give rise to ambiguity, because a processor may consist either of a single core or of a combination of cores. Initially, for some of its enterprise software, Microsoft continued to use a per-socket licensing system. However, for some software such as BizTalk Server 2013, SQL Server 2014, and Windows Server 2016, Microsoft has shifted to per-core licensing. 21. Oracle Corporation counts an AMD X2 or an Intel dual-core CPU as a single processor but uses other metrics for other types, especially for processors with more than 2 cores. 22. Embedded applications. An embedded system on a plug-in card with processor, memory, power supply, and external interfaces. Embedded computing operates in an area of processor technology distinct from that of mainstream PCs. The same technological drives towards multi-core apply here too. Indeed, in many cases the application is a natural fit for multi-core technologies, if the task can easily be partitioned between the different processors. In addition, embedded software is typically developed for a specific hardware release, making use of software portability, legacy code or supporting independent developers less critical than is the case for PC or enterprise computing. As a result, it is easier for developers to adopt new technologies, and as a result there is a greater variety of multi-core processing architectures and suppliers. Network processors. As of 2010, multi-core network processors have become mainstream, with companies such as Freescale Semiconductor, Cavium Networks, Wintegra and Broadcom all manufacturing products with 8 processors. For the system developer, a key challenge is how to exploit all the cores in these devices to achieve maximum networking performance at the system level, despite the performance limitations inherent in asymmetric multiprocessing (SMP) operating system. Companies such as 6Wind provide portable packet processing software designed so that the networking data plane runs in a fast path environment outside the operating system of the network device. 23. Digital signal processing. In digital signal processing the same trend applies. Texas Instruments has the 3-core TMS 320C 6488 and 4-core TMS 320C 5441. Freescale the 4-core Master of Science 8144 and 6-core Master of Science 8156, and both have stated they are working on 8-core successors. Newer entries include the Storm 1 family from Stream processors, Inc. with 40 and 80 general-purpose ALUs per chip, all programmable in C as a SIMD engine, and Pica chip with 300 processors on a single die, focused on communication applications. Heterogeneous systems. In heterogeneous computing, where a system uses more than one kind of processor or cores, multi-core solutions are becoming more common. Xilinx ZYNQ Ultrascale and UTSOC has a quad-core ARM Cortex-A53 and dual-core ARM Cortex-A5. Software solutions such as OpenAMP are being used to help with interprocessor communication. Mobile devices may use the ARM Big. Little architecture. Hardware examples. Commercial. Adaptiva Epiphany, a many-core processor architecture which allows up to 4096 processors on chip, although only a 16-core version has been commercially produced. Aeroflex Gazela Leon 3, a multi-core SPARC that also exists in a fault-tolerant version. AGI PHYSX, a multi-core physics processing unit. Ambricum 2045, a 336-core massively parallel processor array, MPPA. And a series, dual, triple, and quad-core of accelerated processor units, APU. Athlon 64FX and Athlon 64X2 single and dual-core desktop processors. Athlon 2, dual, triple, and quad-core desktop processors. FX series, quad, 6, and 8-core desktop processors. Optron, single, dual, quad, 6, 8, 12, and 16-core server /workstation processors. Phenom, dual, triple, and quad-core processors. Phenom 2, dual, triple, quad, and 6-core desktop processors. Sempron, single, dual, and quad-core entry-level processors. 24. Turion, single and dual-core laptop processors. Ryzen, dual, quad, 6, 8, 12, 16, 24, 32, and 64-core desktop, mobile, and embedded platform processors. EPYC, quad, 8, 12, 16, 24, 32, and 64-core server and embedded processors. Radeon and Firestream multi-core GPU /PU, 10 cores, 16 5-ish U-wide superscalar stream processors per core. Analog Devices Blackfin BF561, a symmetrical dual-core processor. ARM MP Core is a fully synthesizable multi-core container for ARM 11 MP Core and ARM Cortex-A9 MP Core processor cores, intended for high-performance embedded and entertainment applications. ASOC's Modem X, up to 128 cores, wireless applications. Agile Systems Vega 1, a 24-core processor, released in 2005. Vega 2, a 48-core processor, released in 2006. Vega 3, a 54-core processor, released in 2008. Broadcom Cybyte SB1250, SB1255, SB1455, BCM 2836 quad-core ARM SoC, designed for Raspberry Pi 2. Cadence Design Systems Tensilica Extensor LX6, available in a dual-core configuration in Espressif Systems SESP32. ClearSpeed X700, 192-core processor, released in 2008, 32/64-bit floating point, integer ALU. Cradle Technologies CT3400 and CT3600, both multi-core DSPs. Cavium Networks Oction, a 32-core MIPS MPU. Coherent Logix HX3100 processor, a 100-core DSP/GPP processor. Freescale Semiconductor IQ series processors, up to 8 cores, Power ISA MPU. Hewlett-Packard PA 8800 and PA 8900, dual-core Power ISC processors. IBM Power 4, a dual-core Power PC processor, released in 2001. Power 5, a dual-core Power PC processor, released in 2004. Power 6, a dual-core Power PC processor, released in 2007. Power 7, a 468-core Power PC processor, released in 2010. Power 8, a 12-core Power PC processor, released in 2013. Power 9, a 12 or 24-core Power PC processor, released in 2017. Power 10, a 15 or 30-core Power PC processor, released in 2021. Power PC 970MP, a dual-core Power PC processor, used in the Apple Power Mac G5. Xenon, a triple-core, SMT-capable, Power PC microprocessor used in the Microsoft Xbox 360 game console. Z10, a quad-core Z/architecture processor, released in 2008. Z196, a quad-core Z/architecture processor, released in 2010. ZEC12, a 6-core Z/architecture processor, released in 2012. Z13, an 8-core Z/architecture processor, released in 2015. Z14, a 10-core Z/architecture processor, released in 2017. Z15, a 12-core Z/architecture processor, released in 2019. Telum, an 8-core Z/architecture processor, released in 2021. Infineon AURIX. Danube, a dual-core, MIPS-based, home gateway processor. Intel Atom, single, dual-core, quad-core, 8, 12, and 16-core processors for netbooks, NetOps, embedded applications, and mobile internet devices, MIDS. 25. Atom SoC, system on a chip, single-core, dual-core, and quad-core processors for smartphones and tablets. 26. Celeron, the first dual-core, and, later, quad-core, processor for the budget/entry-level market. 27, 28. Core Duo, a dual-core processor. 29. Core 2 Duo, a dual-core processor. 30. Core 2 Quad, 2 dual-core dies packaged in a multi-chip module. 31. Core i3, Core i5, Core i7 and Core i9, a family of dual, quad, 6, 8, 10, 12, 14, 16 and 18 core processors, and the successor of the Core 2 Duo and the Core 2 Quad. 32. Itanium, single, dual-core, quad-core, and 8-core processors. 33. Pentium, single, dual-core, and quad-core processors for the entry-level market. 34. Teraflops research chip, Polaris, a 3.16 GHz, 80-core processor prototype, which the company originally stated would be released by 2011. 35. Xeon Dual, Quad, 6, 8, 10, 12, 14, 15, 16, 18, 20, 22, 24, 26, 28, 32, 48, and 56 core processors. 36, 37, 38, 39, 40, 41. Xeon Phi 57, 60, 61, 64, 68, and 72 core processors. 42, 43. Intelisys Seaforth 40C18, a 40-core processor. 44. Seaforth 24, a 24-core processor designed by Charles H. Moore. Calray MPPA 256, 256-core processor, released 2012, 256 usable VLI cores, network on chip, no C. 32/64-bit IEEE 754 compliant FPU. NetLogic Microsystems XLP, a 32-core, quad-threaded MIPS 64 processor. XLR, an 8-core, quad-threaded MIPS 64 processor. XLS, an 8-core, quad-threaded MIPS 64 processor. NVIDIA GeForce 9 multi-core GPU, 8 cores, 16 scalar stream processors per core. GeForce 200 multi-core GPU, 10 cores, 24 scalar stream processors per core. Tesla multi-core GPU, 10 cores, 24 scalar stream processors per core. RTX 3090, 10,496 CUDA cores. Pew cores winking sad smiley 3, plus other more specialized cores. Parallax Propeller P8X32, an 8-core microcontroller. Pico chip PC200 series 200-300 cores per device for DSP and wireless. Plurality HAL series tightly coupled 16 to 256 cores, L1 shared memory, hardware synchronized processor. Rapport Keeler Core KC256, a 257-core microcontroller with a PowerPC core and 256 8-bit processing elements. Cortex Node has 6 MIPS 64 cores on a single chip. Sci5. U74 includes 4 cores. Sony/IBM/Toshiba's Cell processor, a 9-core processor with 1 general-purpose power core and 8 specialized SPUs, synergistic processing unit, optimized for-vector operations used in the Sony PlayStation 3. Sun Microsystems MAJC 5200, 2-core VLI processor. Ultra SPARC4 and Ultra SPARC4 Plus, dual-core processors. Ultra SPARC-T1, an 8-core, 32-thread processor. Ultra SPARC-T2, an 8-core, 64 concurrent thread processor. Ultra SPARC-T3, a 16-core, 128 concurrent thread processor. Spark T4, an 8-core, 64 concurrent thread processor. Spark T5, a 16-core, 128 concurrent thread processor. Sunway SW26010, a 260-core processor used in the Sunway Taiyu Lite. Texas Instruments TMS320C80 MVP, a 5-core multimedia video processor. TMS320C66, 248-core DSP. Tyler TILE64, a 64-core 32-bit processor. Tile GX, a 72-core 64-bit processor. XMOS software-defined silicon quad-core XS1G4. Free. OpenSPARC. Academic. MIT, 16-core raw processor. University of California, Davis, asynchronous array of simple processors, ASAP, 36-core 610 MHz ASAP. 167-core 1.2 GHz ASAP2. University of Washington, wave-scalar processor. University of Texas, Austin, TRIPS processor. Linköping University, Sweden, EPUMA processor. UC Davis, Keeler Core, a 1000-core 1.78 GHz processor on a 32nm IBM process, 45. Benchmarks. The research and development of multi-core processors often compares many options, and benchmarks are developed to help such evaluations. Existing benchmarks include Splash2, PARSEC, and Cosmic for heterogeneous systems. 46. See also: CPU shielding, CUDA, PU, hyperthreading, MNI-core, multi-core association, multitasking. OpenCL, Open Computing Language, a framework for heterogeneous execution. Parallel Random Access Machine. Partitioned Global Address Space, PGAS. Race Condition. Thread. Notes. 1 carat digital
Yes, I don't think we can read the notes because we already are in the part 3.
See also: CPU shielding, CUDA, PU, hyperthreading, MNI-core, multi-core association, multitasking. OpenCL, Open Computing Language, a framework for heterogeneous execution. parallel random access machine. Partitioned global address space, PGAS. Race condition. Thread. Notes. 1-carat digital signal processors, DSPs, have used multi-core architectures for much longer than high-end general-purpose processors. A typical example of a DSP-specific implementation would be a combination of a RISC CPU and a DSP MPU. This allows for the design of products that require a general-purpose processor for user interfaces and a DSP for real-time data processing. This type of design is common in mobile phones. In other applications, a growing number of companies have developed multi-core DSPs with very large numbers of processors. 2-carat 2 types of operating systems are able to use a dual CPU multiprocessor, partitioned multiprocessing and symmetric multiprocessing, SMP. In a